Hello, students, and welcome. Today, we're going to talk about a topic that sometimes seems a little tricky, motion graphs. But I want to assure you, they're not difficult at all. In fact, they are a wonderful visual way to understand how things move. So, let's get started and see how simple they really are. Just imagine you're watching a car as it starts, speeds up, and then slows down for a traffic signal. Now, what if I told you that this entire journey, this whole story, could be captured and understood just by looking at a simple line on a graph? That is exactly what motion graphs do for us. They tell us the story of motion.
Now, I know some of you hear the word graphs and you immediately think of maths and get a little worried, but please don't. You have already worked with graphs in your mathematics class, right? These are exactly the same. The only difference is that instead of just plotting numbers, we are plotting the journey of an object. They are pictures that tell a story.
So, here is our plan for today's lesson. We'll first quickly see why we even use these graphs. Then we will learn how to read distance time graphs. After that, we will move on to velocity time graphs. We'll also uncover a neat trick to find the distance from these graphs. And finally, we will solve a problem to make sure we've understood everything.
Okay, let's begin with our first type of graph, the distance time graph. Think of this as the first, and maybe the simplest, chapter in our story of motion. Understanding this one well will make everything else much, much easier.
Now, the first rule, the most basic rule, is to know what goes where. For a distance time graph, we always put time on the horizontal x-axis, and the distance covered by the object goes on the vertical y-axis. This setup is fixed, so it's a good idea to remember it.
So, what does it look like when an object is moving at a steady, constant speed? We call this uniform speed. On a distance time graph, this journey looks like a perfectly straight line sloping upwards. This straight line tells us a simple thing. For every second that passes, the object covers the exact same amount of distance. Now look at how steep that line is. In physics, we call this steepness the slope. And for a distance time graph, the slope has a very special meaning. It tells us the speed of the object. A steeper line means a higher speed, and a less steep or gentler line means a slower speed. Simple, right? Here's a good question for you to think about. We've seen a sloping line for a moving object, but what if the line on the graph is not sloping at all? What if it's completely flat, a horizontal line? What kind of motion, or non-motion, is that telling us about?
Well, if the line is horizontal, look at what's happening. Time is passing. The value on the x-axis is increasing, but the distance on the y-axis is not changing at all. If the distance is not changing, what does that mean? It means the object is not moving. It is stationary or at rest, so its speed is zero.
But in real life, we rarely move at a perfect, constant speed. Think about riding a bicycle in traffic. You speed up, you slow down, your speed keeps changing. This is non-uniform speed. On a distance time graph, this kind of journey is shown by a curved line. Because the line is curving, its steepness is changing at every point, which tells us the speed is also changing.
Okay, so we've got the hang of distance time graphs, but what if we want to understand acceleration, that is, the change in speed? For that, we need a more powerful type of graph. Let's move on to our next chapter, the velocity time graph. This is where things get really interesting.
Right, now I need you to pay very close attention here. This is a small change, but it's very important. On a velocity time graph, the x-axis is still time, no change there. But the y-axis is now representing velocity, not distance. This one change makes the graph tell a completely different story.
So let's think. Remember what a flat horizontal line meant on the distance time graph? It meant at rest. But here, on a velocity time graph, a flat horizontal line means the value of velocity is not changing. It means the object is moving with a constant, uniform velocity. See the difference? This is very important.
Now, what if the object is speeding up, but at a steady rate? We call this uniform acceleration. On a velocity time graph, this looks like a straight line sloping upwards. It shows that the velocity is increasing by the same amount in each second. And guess what the slope of this line gives us? It gives us the acceleration.
And of course, if you can speed up, you can also slow down. When an object is slowing down at a steady rate, we call it uniform deceleration. On the graph, this is shown by a straight line that slopes downwards. A downward slope simply means that the velocity is steadily decreasing over time, like when a driver applies the brakes smoothly.
All right, velocity time graphs are great for understanding acceleration, but they have another secret.
Another very useful feature. They can also tell us the total distance an object has traveled. Let's see how we can unlock this secret.
And here is the secret. The distance traveled by the object is equal to the area of the region enclosed under the velocity-time graph line and the time axis. I'll repeat that. The area under the graph gives you the total distance. This is a very powerful idea that we can use to solve many problems.
So, how do we find this area? Well, you just look at the shape formed between the graph line and the time axis. Sometimes it will be a simple shape, like a rectangle. That happens in uniform velocity. Or maybe it's a triangle, which you get in uniform acceleration from rest. Sometimes it might be a more complex shape, but you can usually break it down into simple rectangles and triangles. Just find the area of those shapes and you found the distance.
Now, students, this is a very important point and a very common place to make a mistake in exams. So please, listen carefully. For a velocity time graph, the slope gives you acceleration, and the area under the graph gives you distance. Please do not get these two mixed up. Slope is acceleration, area is distance. Theory is good, but the best way to really learn something is to apply it. So, let's put all this knowledge together and use it to solve a typical problem just like you might see in your textbook or your exam.
Here is our problem. It's from your NCERT textbook. A train is starting from rest, so its initial velocity is 0. It reaches a velocity of 72 kilometers per hour in 5 minutes. We need to find two things. First, the acceleration, and second, the distance it traveled to reach that speed.
Okay, let's solve this step by step. The first step is always to write down what we know. The initial velocity, u, is 0. The final velocity, v, is 72 kilometers per hour, which is 20 meters per second. And the time, t, is 5 minutes, which is 300 seconds. For acceleration, we use the formula a equals v minus u divided by t. So that's 20 minus 0 divided by 300, which gives us 1 upon 15 meters per second squared. Now for distance. We can use the formula 2as equals v squared minus u squared. Rearranging for s, we get s equals v squared divided by 2a. Plugging in the values, we have 20 squared divided by 2 times 1 upon 15. This calculates out to 3,000 meters.
So there we have our answer. The train traveled a distance of 3,000 meters, which is, of course, 3 kilometers. See? By breaking the problem down into simple steps and using the right formulas, we can solve it quite easily. Well done.
So, let's quickly summarize what we learned today. For a distance time graph, the slope gives us the speed. For a velocity time graph, the slope gives us acceleration, and the area under the graph gives us the distance. Remember these 3 key points. Mastering these graphs is absolutely essential because they form the foundation for the next topic we will study, the 3 equations of motion. Thank you, and keep practicing.